Okay, welcome to lecture. We'll get started here in just a second. We're continuing on where we left off in chapter 2. So if you can, just like normal, just type here into the chat box and we'll get started here in just a second, picking up where we left off. And like usual, if you have any questions throughout the lecture, feel free to ask them in that chat box where you're typing here for the attendance right now. Okay, so we are in chapter 2. We've been talking about energy, waves, wavelength, frequency, and we left off sort of talking about electrons as they transition from one energy level to the next, sort of through the Bohr model. And again, remember the Bohr model is sort of that planetary model where we have electrons traveling around in these fixed areas around the nucleus, which are known as orbits, and these circular sort of patterns. Remember that they could only transition from one energy level to the next, which accounts for those sort of line spectrums that we see, for example, in hydrogen. And also you saw in the video and kind of like what happens in sort of the flame test as well that we did. As they again transition from one energy level to the next, the energy level is that n number, which is really the principal quantum number. And as they transition from one to the next, either up in energy, lower in energy, they do have to give off or absorb enough energy basically to make that full transition from one orbit to the next. As we also talked about towards the end, not correct or holds up very well his model or theory of the atom. Past hydrogen, we get more electrons involved. But again, as we talked about, does sort of explain the lines that we do see in the spectrum for hydrogen and the colors that we sort of see as well. So at the end there, we were talking about sort of some calculations, and we had the delta E is equal to minus 2.18 times 10 to the minus 18 joules. What is with this, right? It just does not like this slide. It's still can't do it. 1 over n final squared minus 1 over ni squared. And again, that was Rydberg's constant there, that 2.18 times 10 to the minus 18, which is what is over here. Let's try that again, maybe. There we go, a little bit better. And remember, we could use this formula here to figure out the energy change in the atom as the electrons are transitioning from one energy level to the next. And again, F is our final energy level, NF, Ni is our initial. So again, we had an example earlier there that went from like 5 to 2, for example. So if we did that, we could put that in. Now our final here would be 2. So that would be 2 squared, which would be 4, minus 1 over our initial, which would be 5 squared. There's just something it does not like about this slide. And obviously when we could do that, we will put that in like we did previously. And that gives us something like the change in energy, as I think we did last time, was it's not move there. It doesn't like the minus part. Huh? All right, so it's minus 19 joules. And as we talked about last time, we can sort of relate this equation here to our other ones that we've seen before, which is R equals H times V, R equals HC over the wavelength. And we could use it obviously to calculate the wavelength as well. I'm going to stop writing negatives. Apparently it doesn't like this slide. That's 2 days in a row it hates this slide. So, so those are the calculations that we sort of did there. And again, we could tie those together for the ones we saw earlier, like our C equals the wavelength times the frequency as well. So a lot of those that you did in that experiment yesterday in terms of those calculations, you know, will allow you to figure out all kinds of things, energy change, wavelength, frequency. Remember, as we talked about last time, a couple important things when you're doing these calculations. When you do calculate energy, you should, again, if it is negative, leave the negative sign. Or obviously, if it's positive, you should leave the positive sign. But as we talked about, when you go continue on, perhaps you use that energy in another calculation to calculate something like frequency or wavelength. Remember that frequency and wavelength, they should be positive numbers. So when we talk about the energy part of it, we do keep that negative there. Again, because that indicates if it is negative, it's exothermic, which as we talked about means heat and energy is released in that process. While if it's a positive value for energy, again, that means that heat and energy is absorbed. So the negative sign is really important for the energy part of the calculation because it does allow people to understand if it's exothermic or endothermic. But in terms of continuing on, like we talked about and using it, you do want to make sure you obviously get rid of it because you should not end up with a negative wavelength or a negative frequency. Now, like some of you saw, frequency does become usually a pretty large number when you do the calculations. So some of you were surprised by that, but it does become a lot of times a very large number. So for example, I think in the experiment, you were on the order of something like times 10 to the 14 or something like that in terms of the number. And also the other thing that some of you saw, right, as well is you want to, again, definitely make sure that you are using your exponent button when you punch these numbers in. Otherwise, you will find yourself sort of off, especially in the sort of exponent part of the answer and stuff like that. Any questions on that stuff we were talking about previously here? All right. So we've been talking sort of about this idea of a little bit of the dual nature of particles such as electrons. Again, they are particles, so they do behave like particles, but they also have been shown to sort of particles like electrons have been shown to have some wave function sort of characteristics. And a guy by the name of de Broglie came up with sort of an idea that he proposed that, again, if particles could basically have some wave character function, you know, waves also could have particle type functions. And he came up with this idea here in this calculation or this formula that we see here. This is what's sometimes referred to as the de Broglie wavelength. And this is the formula down here. It's actually missing an S. So right here should be an S for seconds. So you might want to add that in. So there should actually be an S over there. And this is the Broglie wavelength. He actually didn't do, my understanding, if I remember correctly, he didn't do any actual experiments or anything. He just sort of theoried it, and it sort of was proven correctly here. And he sort of thought of waves that could be like standing waves. And what that means is, like, again, if you kind of pluck a guitar string, right, the string is sort of bolted in on both sides. So you kind of see the wave kind of go as sort of almost like a standing wave. And there's points where that wave will have no amplitude. So like where zero pretty much. So as the wave comes down, sort of stops and it's zero in terms of its amplitude, which is, again, the height of the wave. And you calculate the de Broglie wavelength by what we got down here. The wavelength, which will be in meters in this case, equals h divided by the mass times the velocity, which would be in meters per second. So we do see some different units in here for h. And if you remember, h is joules times seconds. And if you also remember, I think we saw at the very end of chapter 1, a joule is equal to a kilogram meters squared over seconds squared. And that's where this comes from here. So this part of the units are really joules. So again, another way of expressing joules is in kilograms meters squared seconds squared. Here we're going to use that sort of version of the joules in terms of units so that everything will cancel out. And that's why, again, there is actually an extra seconds right over here. And because it's joules times seconds, so that's why the seconds should be there. And when we look at the units, a couple of things are important because the joules are really in kilograms per meter squared per second squared, or divided by second squared. That means that when you get the mass of the object, the particle that you're dealing with, be it an electron, a proton, whatever it may be, or a baseball, basketball, whatever it could be, a golf ball, you do want the mass to actually be in kilograms so that it cancels out. So that's an important part when you use this specific equation. When you do mass, it has to be in kilograms in order for everything to properly cancel out. The velocity is in meters per second. And what that will essentially do, if we just kind of look at the units here, up on top, we have our kilograms, our meters squared, our seconds squared. It's a bad M. Over here we have seconds divided by kilograms on the bottom, meters per second. So a second here cancels out second there cancels out second there. Kilograms takes care of a kilogram there, and a meter cancels out one of the meters there. So the only unit left when it's all said and done is meters. The good news is it's really just the units that are different. So H is still the same Planck's constant that you used in all those calculations yesterday, 6.63 times 10 to the minus 34 joules seconds. And it's still that same number that you use. So it's just the units are different. So you can even use it still as joules per second as long as you understand and remember that when you're using this equation, you need to make sure that that mass gets into kilograms so everything properly cancels out. So you don't want to leave it in grams. Any questions on that there? Okay, so I think we got one. So why don't you give one a go here? So why don't you take a minute or two here and give this a calculation here. We're looking for the wavelength of an electron that's traveling at 2.65 times 10 to the 6 meters per second. Okay, so let's take a look and see how we're doing. So in this particular case, again, we want to calculate the Broglie wavelength. So we want to use the formula which is there on the screen. So we have the wavelength equals h over m times v. Again, h being Planck's constant. So when we put Planck's constant in there, that's our 6.63 times 10 to the minus 34 joule seconds. So remember, joule seconds is kilograms meters squared second squared, and that's going to still be times seconds as well. So that's a minus. We're going to divide it by the mass. In this particular case here, the mass was given to us in kilograms, so we're all good in terms of that. A reminder again, if it's not given to you in kilograms, you do need to convert it to kilograms so the units cancel. And that would get us 9.11 times 10 to the minus 31 kilograms. And our velocity also in the right units as well. Again, may not always be in the right units. So in this case, they are meters per second. So it may require you, again, a conversion there as well. And that would get us 2.65 times 10 to the 6 meters per second. All right. Now, in terms of units, we're good. Our kilograms are going to cancel. Our seconds and seconds are going to cancel. And again, one of our meters are going to cancel. So again, we have a lot of numbers here in scientific notation. So a reminder, we do want to make sure that we do use the exponent button for sure. Yeah. So remember that when we do use the exponent button, you don't have to hit the multiplication button or anything like that. So when it puts like a little E up there, as we talked about, I think yesterday, that E represents the times 10 part of the number. So no need for multiplication, no need for the caret, the 10, anything like that. You just hit that. So as you type this in, for example, you would probably want to hit 6.63 exponent button, negative button, and 34, and divide it by 9.11 exponent button, negative button, and 31. Since there's multiple things to divide by, something that always happens for people as well, they try to put everything in at once, and they oftentimes will get the wrong answer because they don't put parentheses correctly and stuff like that. So I would recommend, like I just did there, I took the top number and divided by the first bottom number, and I would hit equals at that point, and then divide it one more time by the second number, 2.65 exponent button and 6, and hit equals again. And when you do that, you will end up with, hopefully, a 2.75 times 10 to the minus 10. And again, the unit here would be meters. Any question on that calculation? So again, you got to really try to get into the habit of using your exponent button. And if you have lots of stuff to divide by, I find it's best to multiply as many things you want on top and hit equals at the end, and then divide by the first guy on the bottom, hit equals, divide by the second guy on the bottom, hit equals, and you usually will end up with the right answer. Again, sometimes people try to put in a ton of numbers at once in their calculator, and sometimes it does it wrong. Yeah, so it's really, so the question was, why are we using kind of those different units for Planck's constant? And it's really just so you could see that all the units sort of cancel out and what's left over. Truth be told, you can still use the same units if you like, the joules times the seconds. And a joule is just known to equal what we were talking about on the last slide. A joule is equal to a kilogram meter squared second squared. So instead of a joule, you could actually use those units. And the reason we sometimes use those units here is because we have the kilogram on the bottom, we have the meters and seconds on the bottom. So that lets you kind of visually see all the units canceling out. If you want, there's nothing really wrong technically with leaving it as joules times seconds, as long as you remember that when you're using this equation, technically speaking, the mass needs to be in kilograms and the velocity needs to be in meters per second. So if you want, you can still leave it as joules per second like we did last time, but sometimes it's good to remember that relationship, because then it will help you, hopefully help trigger you, like I should have the mass in kilograms and the other guy should be in meters per second, so you can kind of remember everything cancels out. In terms of the actual value, it has no effect on the value of Planck's constant. It's still the same number. It's just a sort of another way of expressing the units. Other questions? Okay. So as we've been talking a little bit about sort of Bohr's model or theory of the atom, which is that orbital orbit model, where those electrons are traveling around those pretty circles around the nucleus. And again, as we talked about, as you move away from hydrogen and more electrons get involved, it doesn't really hold up very well. And some experiments and stuff were done, and sort of a principle came about, which is known as the Heisenberg uncertainty principle, which says that there's sort of a fundamental limitation about how precisely you can know exactly where a particle, like an electron, for example, both its position and its momentum, how it's moving, basically. So the more you sort of know about one aspect of that, the more you know about sort of the location of an electron, the less you know about sort of the way it's moving. And what this was sort of a big step forward was the idea of where we had for Bohr, the idea of orbits and that sort of planetary model where they're just moving around in these nice circles, to sort of moving away from that and move into a more quantum mechanical model where we think about electrons as being in things known as orbitals. And what orbitals really are sort of probability maps of where you could find a high probability of finding an electron in an atom, for example. And as we'll talk about here in this chapter, the rest of it, there's s orbitals, p orbitals, d orbitals, f orbitals. And again, these are more probability maps. Are probabilities of where to find an electron. So down on the bottom here is sort of the Heisenberg's uncertainty principle. We're probably not going to do pretty much any calculations that involve this formula here or equation, but just so you have an idea what it is, delta x is the uncertainty in sort of the position of a particle like an electron, and delta mv is the uncertainty in sort of how fast that particle is moving, and h is our Planck's constant, and pi is obviously pi. And again, this is the sort of the relationship and equation that helped us sort of move away from Bohr's idea of orbits into this more probability map, as we will see. And the idea behind these is essentially this idea: we do have our nucleus, right? And in our nucleus is our protons, which are positively charged. We have our electrons out from the nucleus at some point. We again don't really know how they're traveling. They are traveling pretty randomly about it, but there is some places where we could have some good probability of finding an electron. And we know that because the opposites attract, the positive is attracted to the negative, that these electrons, there's a pretty high probability, probably near the nucleus. Not really sure where that's at, but there's a pretty high probability that an electron could be found in that area. And a little hard to do with this pen, but as we sort of move away from that, it gets a little bit less and less of a probability of sort of finding an electron out from there. So we'll see some little bit of some probability sort of maps in a bit here, but usually they're kind of displayed by color. Sort of darker areas is a higher probability of finding something like an electron. As the color sort of gets lighter, as you kind of fan out from the nucleus, there's a lower probability, of finding a particle like an electron that's there. So Heisenberg's uncertainty principle was a major sort of step forward of moving to a more quantum mechanical model where we look at these things as sort of probabilities of finding particles like electrons. And again, moving away from the idea of electrons traveling these pretty little circles around the nucleus and stuff like that. Again, they do travel at pretty random sort of patterns and motions. So that's where we get into this idea of moving towards sort of this probability. And a guy by the name of Schrodinger came up with a whole bunch of equations, sort of derivatives and those type of guys, to indicate sort of probability of where you could find a particle like an electron, since it does have some wave function to it, in terms of high probability, low probability. If you want to learn more about those equations, you ever take physical chemistry, that's all you do for like the first semester, is you deal with all of that in the physical chemistry, all those wave functions, derivatives, calculus, all that fun stuff. So here we see sort of a probability distribution for a 1s orbital. And let's just talk a little bit about sort of the orbitals here, where we find electrons. In terms of orbitals, again, these are these sort of probability map. And every orbital, every individual orbital is where we can sort of hypothetically think an electron is in an atom. And every individual orbital can only hold a maximum of 2 electrons. And so the types of orbitals that we have, as I put on the other slide, there's s orbitals, there's p orbitals, there's d orbitals, and there's f orbitals. And each of these orbitals have a different amount on each of these energy levels. So no matter where you go on any energy level, there's only one type of s orbital that you'll find. And we'll see what it looks like in a second. On any energy level where p orbitals exist, there's actually 3 different types of p orbitals that exist. On any energy level that you find d orbitals, there's actually 5 different d orbitals that exist. And on any energy level where you find f orbitals, there are 7 different f orbitals that exist, which means if we max out these guys in terms of maximum electrons, since each one can only hold 2 electrons and there's only one type of s orbital, 2 is our total number we could have there. If we max out all 3 of the different p orbitals and each one could hold 2, we can max out at 6. And if we max out the Ds, each one could hold 2, and there's 5 of them, we can max out with 10 electrons and 14 electrons there for our 7 f orbitals that occur. These guys, as we'll talk about here, are sometimes what are referred to as subshells or sublevels. And we'll talk a little bit more about that. So an s orbital, for example, here's sort of a probability map based on, probability and distance from the nucleus. And what you can see here is a much better drawing of what I was trying to draw on the red pen earlier. We see very dark color, in this case blue. A lot of times it's pink or red, but we see a really dark color blue towards the center. And we can sort of envision that the nucleus is, right about there. Right? And because the nucleus is right about there, we would expect to have a very high probability of finding an electron in that area. Now, remember, Heisenberg's uncertainty principle tells us we don't know exactly where the electron is or exactly how it's traveling or where it is at any given point in time. But there is a pretty high probability that at some point in time, we would find an electron in that area of the atom. As you can see, as you sort of fan out away from the nucleus in this area, the color gets a lot lighter. And we can also see that on the graph as well. The percentage in terms of probability decreases a lot as we head away from the nucleus. So what that also tells us is there's a very kind of lowish probability, if you will, of finding an electron out in that outer region. A lot of them are going to try to get as close to the nucleus as possible, but it's still blue out there. So there are still some electrons out there. And as we'll talk about, those are the higher energy electrons. Those are like your valence electrons, the guys involved in bonding that are found out on the fringes and stuff like that. But a little bit lower of a probability of finding a lot of electrons in that area. So again, this is all about sort of moving away from Bohr's model into this sort of orbital model of where we find these guys, electrons in an atom. And here again is sort of an overlay. And again, you can kind of see as you fan out from the nucleus, it gets much, much smaller. So orbitals in terms of size are difficult to define precisely. Orbitals are really wave functions, and we really don't get way into wave functions or anything like that. And like I said, if you ever take physical chemistry for a semester, that's all you talk about is wave functions and stuff like that. But we sort of picture an orbital as sort of a 3-dimensional sort of electron density map. And there's areas within these orbitals where, again, you have to find a higher probability of finding those electrons. And for example, an s orbital, no matter what energy level you are on, basically an s orbital is a sphere. And it's just sort of a circle there. And as you go from one energy level to the next, it just gets bigger, but still sort of the same sort of overall shape in terms of what we think about in terms of an S. And in an S, you know, again, you can kind of envision the nucleus in the center of it. Again, a higher probability sort of in this area. And again, as you fan out to the edges there, a little lower of a probability. And these orbitals are sort of different in sort of three-dimensional sort of size or shape, if you will. For example, I'll just draw p orbitals. P orbitals look like figure eights, basically. And there's three different sort of figure eights that sort of occur. And again, in this sort of idea, you could kind of visualize the nucleus in this area. And again, a higher probability of finding electrons probably, you know, in sort of this space as well. D orbitals as well have some different shapes as well. Kind of look like two p orbitals sort of put together. F's as well have different shapes as you go through it. So let's talk about sort of ways we can sort of describe where we will find electrons in an atom. And a lot of times we do that with what are known as quantum numbers, which is what's on this slide here. So these are quantum numbers, and there's really four quantum numbers. Let's start with the first one. The first one is n, and we saw a little bit about n the other day, but n is basically the principal quantum number. It is the size and energy of an orbital. So it's really, n is sort of the energy layer, the energy level. There we go. So n is basically your energy level. N could have values of 1 to 7. So for n, you could have a value of basically 1 to 7. The next quantum number is the angular momentum quantum number, and that is abbreviated with an L. And L has the shape of the atomic orbitals. So L also tells you basically what type of orbital you're dealing with, for the lack of a better description. So basically what it's going to tell you, is it an s orbital? Is it a p orbital? Is it a d orbital? Is it a f orbital? So that's basically what L will tell you. Based on the value of L, it will tell you basically what orbital you're basically dealing with. Now, m sub L, by the way, L can have values of 0 to n minus 1. So L can have a value ranging from 0 to n minus 1. M sub L, which is the magnetic quantum number, gives you the orientation of these orbitals in sort of three-dimensional space relative to each other. Another way you could kind of look at M sub L is how many orbitals there are in a subshell. So it really tells you sort of the orientation in three-dimensional space, but it tells you sort of how many there are. And the fourth quantum number, which is not up here, I think we'll see it on a later slide, but we just include it here with this one, is, I'm sorry, I was talking about M sub L first. M sub L can have values of minus L to 0 to plus L. So it could have those type of values. So it runs from minus L, so whatever value you got for L, which is quantum number right before it, negative value to 0 to positive L. All whole numbers are the possible values you could have. And lastly, our M sub S is our spin quantum number. And that basically can have a value of plus or minus 1/2. And really what the spin quantum number tells you is in an individual orbital, how the electrons are spinning. And there's really sort of two designations for that. Plus 1/2 means that when the electron goes in, it's sort of spinning upwards, and we sometimes will represent electrons with arrows. And minus 1/2 basically represents the opposite, that the electron in that particular orbital is sort of spinning downwards, if you will. Electrons have their own spin. They're affected by, obviously, electrical field and magnetic field. And so the sort of designation of how they're spinning is given by either plus 1/2 or minus 1/2. So these are the four different quantum numbers. And really, they are how we get And really what we're talking about here ultimately is electron configuration and sort of how we get to the electron configuration, how we get to how electrons are in the atom of an atom, in the atom there. And perfect. So let's talk a little bit about some of this stuff here. Just kind of move some stuff out of the way so I could kind of see home screen. There we go. All right, so let's talk about sort of what all this means. So when we talk about electrons and electron configuration, right, or how electrons go into the atom, there is an order at which electrons basically go into the atom. And you can use the quantum numbers to help you decide that. So again, n could have values of 1 through 7. L can have values of 0 to n minus 1. And m sub L could have values of minus L. We're doing so well. To 0 to plus L, right? Gosh, it doesn't like that now. And m sub S can have values of 1/2 plus or minus 1/2. All right. So what this means is when we talk about energy levels, if we sort of draw a diagram here, just gonna pop it here, very badly drawn. If this is energy, so if we have n equals 1, which is our first energy level, that, remember, that's the ground state, that's the lowest energy you could have. So let's talk about what happens on the n equals 1. So if n equals 1, there, L can have a value of 0 to n minus 1, which means obviously n minus 1 in this case would be 1 minus 1, which equals 0. And the only value you could have for L is 0. And that means on the first energy level, the only orbital that we have is a 1s orbital. And the 1s orbital refers to, it's on the first energy level. Yeah, I think you're right. I think it's every time I got like a blank slide, it doesn't like it. So maybe I should go back to finding one with something on it. Let me see here. I think you're right. I just don't know if I have one that's empty. Let me see if I can steal one that's empty here. Maybe. We'll steal this one. We'll see. Hopefully it will hold it there. All right, perfect. We'll give that a try. I think you're right as well. So we'll try this one here. All right. So let's see if we're better on this one here, I hope. Yeah. Maybe I just need to throw some stuff into those slides, huh? All right, I'll put a title on them next time. Apparently it doesn't like it. All right, so n equals 1. Thank you very much. So n equals 1. Again, we're going to have our L that can be 0. And what a 0 for L represents is a s orbital. And what that means is when we go to m sub L, it could go from minus L to 0 to plus L. So we will get a value of only 0 for that particular one. And that also tells us that we pretty much only have one type of s orbital here. And in this particular case, the m sub s means it could either be plus or minus 1/2. And what that means is in this orbital here, we could put an electron that's going up. We could put an electron that is going down. And again, the one that's going up is going to be the plus 1/2. The one that's going down is going to be minus 1/2 in this particular case. And that would take care of the first energy level. So when we talk about n equals 1 or n equals 2 or n equals 3, sometimes they're referred to as a level or sometimes they're referred to as a shell. So what we see from our 4 quantum numbers is that only on the first energy level, the only orbital that we see is that s orbital, which is represented by that letter, the L number of 0. So let's see what happens when we go to the second energy level, n equals 2. When n equals 2, that means that L could have again a value of 0 to n minus 1. So in this case, n minus 1 is 2 minus 1, which would be 1. I'm going to do that math, I think, in my head. That means on the second energy level, we should have a value of 0, and we will have a value of 1. And as we just saw earlier, the value of 0 represents an s orbital. The value of 1 actually represents the p subshell. That means on the second energy level, we start to see p orbitals first appear. So we still have our 2s orbital. And if we do the quantum numbers for each of these L's separately, we will get the same row here. We'll get our m sub L, that's 0, and our m sub s, that could be plus or minus a half. And again, that means that we could have an electron up, we could have an electron down in that particular one. Now for our L, which is our P, which is a value of 1, if we did the rest of the quantum numbers for that guy, what we would end up with is an m sub L that can run from, remember, m sub L goes from minus L to 0 to plus L in this case. That means that it runs from minus 1 to 0 to plus 1. So those are all the values that are acceptable for our P subshell. And in each of these, we could have an m sub s of plus or minus 1/2. So what does this mean? If you know, or if you remember electron configuration from the class you took before, there are 3 different types of P suborbitals, right? And that's a px, right, a py, and a pz orbital. Those are really where they are in 3-dimensional space. And that's what each of these numbers represent. This represents the px orbital. This guy represents the py orbital. And this number represents the pz orbital. So what that tells us, if we filled it in, we would have sort of 3 lines, if you will, to represent the 2p subshell. And in each of those orbitals, we could have an electron up, an electron down, and each of those, again, the one in the up direction would be plus 1/2 for our m sub s, and again, the arrow going down would be represented by minus 1/2 for m sub s. Now, if we continue on to our n equals 3 level, with n equals 3, L could have a value again of 0 to n minus 1. So in this case, n minus 1 would be 3 minus 1, which would be 2. And that means that we have 0, 1, and 2. So I won't redo these, but these 2 guys here are the exact same things we just did over here. And that means that when we get to the third energy level, that is where we have a 3s orbitals. We also have a 3p or set of orbitals. And now what we will see here is our d orbitals come to appear. And again, an L value of 2 represents a d orbital. And if we just do it for the d orbital part, taking our m sub L, that means it could run from minus 2 to minus 1 to 0 to plus 1 to plus 2. If you add up all those numbers there, the minus 2, the minus 1, the 0, the plus 1, the plus 2, that is 5 numbers. And that is how many d orbitals that we have, right? We have 5 different types of d orbitals. And that's what appears here, 1, 2, 3, 4, 5. And obviously each of those could have an m sub s plus or minus a half. So really bad they drew that there. Any questions on that so far? So these are the quantum numbers that go again with the orbitals. This is also what, based on probability, tells us that on the first energy level, the n equals 1, which is our ground state, there's only 1 orbital present, which is the s orbital. When we get to the second energy level, that's when we start to see our p orbitals start to appear. When we get to the third energy level, that's when we start to see our d orbitals appear over here. And we'll go back one more here, maybe somewhere I didn't scribble. Let's see, short fire. I scribbled a lot, apparently. I'm trying again. Yeah. There we go. Now, if we get to the n equals 4 level, our value of L can go again from 0 to n minus 1. So in this case, n minus 1 would be 4 minus 1, which would be 3, which means you could have values of 0, 1, 2, and 3 in this case. So as we saw previously, our value of 0 is for our s orbitals. Our value of 1 is for our p orbitals. Our value of 2 is for our d orbitals. And as you could probably imagine, our value of 3 is for our f orbitals. So what this tells us is our f orbitals really don't come about until we get to the 4th energy level. So on our n equals 1, we had our 1s. On our n equals 2, we had our 2s, and that's when we first start our 2p's. On our n equals 3, we had our 3s, our 3p's, and our 3d's. And now on our 4th energy level, if we continue on again with just the 3 part of it, the 0, 1, and 2 we did on the previous slide, our m sub L for our 3 can run from -3 to -2 to -1 to 0 to +1, +2, and +3. If you add up all those numbers, you get 7, right? And that is how many orbitals there are in a F or subshell, right? And that means that on the 4th energy level, we have a 4s. We also have our 4p. We also have our 4d. And this is where we first start to see our f orbitals appear. So we could use quantum numbers to really understand on what energy level would we expect to find what type of orbitals present. And again, these are all where we would expect to find electrons in the atom. And as you can kind of see, this is sort of a build-up theory. We're starting at the bottom, and then we're building up more electrons and more electrons and more electrons as you continue upwards in terms of energy. And again, as you go up here in this direction, you are getting higher in energy, and that also means that you are getting further away from the nucleus. So you're going further away from that nucleus over there. Any questions on that? So we could also use quantum numbers to specifically identify the 4 quantum numbers in a specific electron in an atom. And we'll do that as we get through sort of electron configuration and stuff like that. A couple of things, again, just to touch on here with this, while we got it. As I mentioned before, there's some sort of terms that are used when we talk about sort of electrons and where they are in the atom. And so, for example, if we wanted to know how many electrons, if I maxed out the n equals 3 level or shell. So take a moment and try to figure out how many electrons you would have if you max out the n equals 3 level or shell. And then we'll talk about it here. So think about what you come up with there. Okay, so what we're talking about, again, a shell or a level, we're really talking about this guy over here. We're talking about the n number, right? And that means that if we're talking about the n equals 3, we're talking about everybody that is on that level. And if we just add it up there, that is 2, 4, 6, 8, 10, 12, 14, 16, and 18 electrons you would have if you filled up that entire level or shell. Now, what would happen if we want to know how many electrons in, say, How many electrons in the 4p subshell or sublevel? So if we max out, if we sort of want to max out the 4p subshell, think about how many electrons that would be. Right. So if we are, where did I get? I got 18 from here. So I'll just do it right here. Remember that every individual orbital, right, which is represented in my picture here by a line. So every individual orbital could hold a maximum of 2 electrons. So everyone can hold a maximum of 2 electrons. And that means that we would have 2 here, 4, 6, 8, 10, 12, 14, 16, and 18 if we filled up that entire n equals 3 level. Yeah. Well, let's see if we're right there on the next one. So on how many is the maximum electrons in a 4p subshell. So 4p is up here, but remember the subshells are really these guys, yeah? Which means the 4p subshell is really just talking about this set of p orbitals, which means in this case, we could do 2, 4, and 6 electrons to max it out. And again, that's a subshell or a sub level. And so these guys, like I said, these guys are sort of your subshell or level. These guys are sort of your shell or level, it's sometimes referred to. Now, let's do the question that always gets people. How many max electrons in a 4f orbital? So take a second, see what you come up with. Now, when we come up with this 4f orbital, some people may go with the number 14 electrons, right? And that answer in this particular question would not be correct. It would be correct if you asked how many electrons in the 4f subshell, right? That would be 14. But in this particular case, we're looking for just a 4f orbital, which means it could be this orbital, could be this orbital, could be that one, that one, that one, or that one, or that one. But what we just talked about a second ago is any individual orbital that you deal with, no matter what energy level it's on, the maximum number of electrons you could put in there is only 2. So that's usually a trick question that comes about in books and stuff like that. So again, if they're talking about any orbital, sort of individual orbital, the maximum number of electrons you can put in there is only 2. Again, if they said the 4f subshell, then that would be all 14, 2 in each of them. If they said the n equals 4 level, then you would have to add up all those guys. Any questions on sort of those differences in some terms that are used when we talk about these things? By the way, you know, sometimes people don't want to draw all this to figure out how many electrons there are, for example, in a level or a shell. So there is sort of a formula you could use to kind of quickly calculate how many total electrons if you wanted to max out a level or a shell. And that formula is for the max number of electrons in a shell or level, you could do 2 times n squared. So you want to square it first and then times it by 2. So for example, this is the one we did previously. N equals 3. If you take 3 squared and then times it by 2, 3 squared is 9. 9 times 2 is 18. Yeah. If you wanted to do the 4th energy level, 2 times 4 squared. 4 squared is 16. 16 times 2 is 32 electrons. If you filled up every single orbital on this energy level with 2 electrons, you would max out at the 32 electrons here. So that's just sort of a quick way that you can sort of calculate how many electrons, if you want to fill up a shell, or the entire level in that case. Any questions on that? Now, you may also ask, I've only heard of up to F in terms of orbitals. And you said earlier as well that, let's keep going backwards so I find something. Maybe I didn't scribble on too much here. There we go. Now, if you remember, n could have values of 1 through 7, right? Which means we went up to 4. So let's just say, for example, we did n equals 5 on the 5th energy level. On the 5th energy level, again, L could have values of 0 to n minus 1, which means the values of L could be 0, 1, 2, 3, and then 5 minus 1 is 4. And as we saw earlier, this is our s orbitals, this is our p orbitals, these are our d orbitals, these are our f orbitals. And lastly here, what comes next is g. Yeah, so g comes next. It just kind of goes in the alphabetical order. So you just kind of go alphabetical order after that in terms of the orbitals. We never get into like an electron configuration or anything like that that involves anything above f. But they creatively, kind of went alphabetical order after that. So H would be after, for an L value of 5 and so forth. So you just kind of go alphabetical after that. So you could technically come across a question, which then would mean that obviously M sub L for the 4 would go from -4 to -3, -2, -1, 0, to +1, +2. I'm running into people's pictures, 3 and 4 going that way. So you could have all those different types of orbitals available as you continue upwards. Any questions on that particular thing there? Okay. So let's go back to wherever the heck we are now in terms of this lecture. It's like reliving the lecture. It's exciting here. Here we go. All right. Okay, and coming through here. So here's a table, I think from your book as well, or a similar table you have in your book that sort of describes our different sort of values here, our L's, our orbitals, and again, the different types of orbitals that are present there. All right, so for a principal quantum number of n equals 3, determine the number of allowed subshells, the different values of L for each of them. So give it a go there. I know we kind of did it, but just to review, give all the values of L and see what you come up with there. Okay, so as we saw earlier, again, crazy pen, there we go, n equals, and it disappeared. I like that move. All right, so n equals 3, which means, again, L could go from 0 to n minus 1. So that means we could have 0, 1, and 2 in this case. So as we saw, again, that represents our s orbitals, represents our p orbitals, and represents our d orbitals, which are the orbitals that we find on the third energy level. And again, as we saw, that's where we first see the appearance of those d orbitals start to appear. And we sort of did this one as well. So remember that when we do our m sub l, goes from minus L to 0, all whole numbers, to plus L. And that in this case means that we would have minus 2, minus 1, 0, plus 1, and plus 2 as possible values. Again, these represent each of the d orbitals in order, the different types. And by the way, it just represents like those lines that I drew there, for example, 3D. This would be an m sub L of minus 2, minus 1, 0, plus 1, and plus 2. So that's what, each of those sort of lines, they kind of go in order, just like when we were looking at, say, the P. And this would be minus 1, 0, and plus 1 for the m sub L values. So if you sort of draw those little dashes to represent the orbitals, which we'll do for orbital diagram, it just sort of goes in order. The m sub L go left to right, and that's what each one of those sort of boxes represents. Any questions on that? So here is some representations of our 1s, 2s, and 3s orbitals, which are found there. And you can see it's all basically the same size, if you will, or same shape, but they do get larger in size. So as you kind of go up energy levels, the shape does get larger. And you can kind of see a node, again, is sort of an area of a wave, since we're kind of representing these as sort of wave functions. Just to kind of let you know what that is. It's those points where it has no amplitude is really what a node is in a wave function. And that's sort of represented here by the kind of no color zone, if you will, between those zones of where we would find a lot of electrons present. And again, really, this is all sort of probability maps based on sort of calculations and what's known as wave function sort of calculations. And that's what, again, a node is sort of represented of. Again, those darker areas are higher probabilities of finding electrons, just as we talked about, although it does look sort of like that orbit sort of model here. These are just areas of high probability of finding electrons. As you could kind of see, again, kind of closer to the nucleus in this sort of area here, it's a little bit darker. And again, as you get further away, it sort of fans out and gets a little bit lighter. So a little less of a probability of finding electrons in those areas. So this is what our p orbitals look like. And this is our px or py and our pz. And again, you can kind of see that they are essentially figure eights, if you will. Again, the nucleus sort of thought of as being in the middle of this intersection. The x, y, and z notation sort of like in math, right? You got your coordinates there in three-dimensional space, your x, your y, and your z axis. And again, that's where those guys basically will sort of align each other in three-dimensional space. And again, in terms of probability, a lot of times if you see sort of probability, a map of this, kind of a high probability nearish that nucleus in the center, then, it gets a little bit not as dark as you sort of move away from it. These are our d orbitals and what they look like. As you can see, for the most part, they look like a couple of p orbitals that have basically come together. Also, here's our sort of probability map. These darker areas, a higher probability of finding those electrons. Again, you can almost visualize the nucleus sort of in the center of all that along the way here. We also have one that kind of looks like a donut, I think, with a p orbital going through at the end there. But for the most part, they look like a couple of p orbitals that have been put together. And they have also some designations, as you can see, dxy, dx squared, y squared, and so forth. And again, You know, they do represent sort of the those numbers for the m sub l that we see, like -2, -1, 0, +1, and +2 as you go across. And again, that represents sort of those 5 orbitals that are happening. And these are our f orbitals. You can see kind of like 2 p orbitals sort of sorry, 2 d orbitals sort of put together for the most part. And you can see there's 7 different designations of those f orbitals and sort of what they look like. So as I talked a little bit about before, the 4th quantum number, which is that m sub s value, is the spin quantum number. And again, electrons have sort of their own spin when they go into an orbital. And there is a rule for how electrons can go into a particular orbital and how they go in. And one important rule is Pauli's exclusion rule. And Pauli's exclusion rule essentially says that no 2 electrons in the same orbital can have the same 4 quantum numbers. So what does that mean? So we represented these orbitals, right, as sort of these little lines, if you will, right? And if we put an electron in there, we could only put 2 maximum electrons, right? And we're going to represent the electrons by arrows, okay? If I put 2 electrons into this orbital heading in the same direction, let's do the quantum numbers for each of these electrons here. So we'll say that this is the n equals 1, right? Or the 1s orbital. So if this is the 1s orbital, the electron here on the left would have an n value of 1, which means it could have an L value of 0 to n minus 1, which would be 0. And it could have an m sub L, which would also be 0 in this case. Now the m sub s in this case, because it's pointing upwards, that is the plus 1/2 representation. So it would have a value of plus 1/2. And again, this would represent the 4 quantum numbers for this guy right here. Now, if we did it for the guy sitting right next to him in the exact same direction, the n would be 1, the L would be 0, the m sub L would be 0, and just like the one on the left there, the m sub s would be plus 1/2. By putting the electrons into the orbital heading in the same direction, what we get here is 2 electrons that have the exact same 4 quantum numbers. They're identical all the way down. And that is a violation of Pauli's exclusion rule. You can't do that. That same thing happens if you decide to put the electrons both heading downward in that 1s orbital. If you do in that 1s orbital and put them both facing down, the n value would be 1, and that's what this number represents. The L value here would be 0. The m sub L would be 0, and the m sub s would be minus 1/2. And if you did it for the electron on the right, you would hit the exact same numbers. N equals 1, L equals 0, m sub L equals 0, and m sub s equals minus 1/2 in this particular case. And you can again see that in this case, if we put the electrons into the individual orbital heading in the same direction but downward, we still hit the same 4 quantum numbers, which again is also a violation of Pauli's exclusion rule. So what that leaves us is if we want to put electrons into an orbital, we need to actually put them in opposite directions. And if we do the 4 quantum numbers for the guy on the left, it will end up just like we had on the left-hand side. N equals 1, L equals 0, M sub L equals 0, and M sub S equals plus 1/2, again for this guy. And if we did it for the guy on the right, N would equal 1, L would equal 0, M sub L would equal 0. And you may say to yourself, that's 3 for 3 the same. But what makes it different is the spin on that electron. It has a value of minus 1/2. So the 4 quantum numbers here and the 4 quantum numbers here are technically different. They are not the same 4 quantum numbers. And the only difference is the spin quantum number, which allows you to put two electrons into the same orbital, but they need to have opposite spins. So based on Pauli's exclusion rule, when we actually do fill orbitals with electrons, they do actually go in a specific order. When we put them in, the first electron goes up, which has plus a half in terms of the spin quantum number. The second electron goes in down, which has minus a half in terms of the spin quantum number. So the way we sort of get around Pauli's exclusion rule and not violating it is that whenever we do put these electrons into an orbital, they should have opposite spins. Question on that there. So as you can see as well, and as we'll see when we kind of talk about electron configuration, you could get very specific in terms of the quantum numbers. You can pick an individual electron in an atom and go, these are the 4 quantum numbers for that particular electron. And that will give it basically where the location is in the atom, where the spin is, what orbital it is. You could figure pretty much just like an address for your house where you live. You know, you could find exactly where that electron should be in the atom based on its 4 quantum numbers. Any questions on that there? Okay. So atoms with more than one electron, there's sort of a correlation problem that occurs. So since the electron pathways are unknown and there's repulsions that occur, we kind of know exactly, again, where those electrons are traveling or how they're traveling. But when electrons are placed into those sort of quantum levels or the principal quantum numbers, they are placed in a certain order in terms of how the electrons go in. And that order essentially is the electron configuration order that you may be familiar with as well. And what we see is that the 2s electrons penetrate the nucleus more than the 2p. The 2s is lower in energy than, say, the 2p. And even though they're both, for example, these guys, when we talk about it, they're both technically on that n equals 2 level. You have your 2s, you have your 2p. There's actually some differences that occur between the energies in those guys. And actually the 2s ends up being lower in energy, closer to the nucleus than, say, the 2p orbitals. And that affects how electrons go into the atom, because electrons go into the atom in the lowest energy level to the highest energy level, right? So they, just like you're walking stairs, if you're on the ground floor, you go from the first step on the bottom and you keep kind of progressively going upwards until you get to the top. And that's essentially how electrons go into the atom. They sort of build up. So they start at the lowest energy level. If they fill up all the orbitals on that lower energy level, they then go to the next lowest energy level. If they fill up all those guys on the next energy level, then they go to the next one and fill the rest of those up. And they continue to fill up the orbitals from lowest energy to highest energy. As we can see here in this graph, that's just the probability of distribution and how far they could kind of come in. So when we talk about the 3s penetrating more than, say, the 3p, what that essentially means is it's going to be moving itself closer to the nucleus, basically. So it's going to be closer to nucleus, lower in energy. If it doesn't penetrate as far, the orbital is going to kind of stay a little further away from the nucleus, going to be a little bit higher in terms of energy. And there's our orders. So what this means is there's actually a specific order in which we write out something like electron configuration. So why don't we finish up this part of lecture here on that? So let's talk about it. So there's 2 really important things about electron configuration, right? And electron configuration really is the order at which electrons go into the atom. It's the filling order. So the first thing we actually talked about earlier, we need to know that S, P, D, and F, if you max out those sort of subshells and orbitals, you could put 2 electrons, 6 electrons, 10 electrons, and 14 electrons in those guys. And when we have more than one electron, so when we have just one electron, for example, you have your 1s orbital, you have your 2s orbital, your 2p orbital. So when we have just one electron sort of involved, all the orbitals really line up in terms of energy. What that means is everybody on the second energy level is perfectly equal in energy. Everybody on the third energy level also perfectly equal. Everybody on the fourth perfectly equal. But when we start to get more than one electron involved, there's actually a shift in energy that occurs in terms of these orbitals. And the 2s, like I said, becomes lower in energy than the 2p. Again, even though they're technically on the same energy level, there's this shift that occurs. And there's a really big shift that sort of occurs between sort of your order of the 4s, for example, electrons, orbitals, ends up being lower in energy than your 3d orbitals. So that's usually one that kind of confuses people, because you kind of go from 3s and then you go 3p orbitals, and then you would think the d's would come next, but actually the 4s gets in there and then the 3d happens. So there's a lot of shifting that occurs in these orbitals when we get multiple electrons involved. And there is an order. So there's a really kind of easy way to remember the order. If you remember, you just write 1s, 2s, 3s, 4s, 5s, 6s, and 7s, just straight down. And then you go 2p, 3p, 4p, 5p, 6p, 7p. Then you go 3d, 4d, 5d, 6d, and then you go 4f and 5f. And a couple of things. This is the order at which electrons go into the atom. And the way you use this, let's drop a different color in here maybe. Oops. If I hit that button, I think. Is you always start up here at top, and then you kind of follow the arrow, and then you zigzag back, and you just keep following the arrow. And you just keep doing. And you'll see here, if you follow it, you go 1s, zig back to 2s, to 2p, to 3p, to 3p. The 4s comes in first, and then you zigzag back to 3d, 4p, 5s, and then again, you just keep kind of zigzagging back and forth. So you always start up here, and you just keep zigzagging back. And that will allow you to write the electron configuration for anything you need. And that's something that you can kind of create pretty easily for yourself, because if you remember, these orbitals start at n equals 1, 2, 3, and 4 coming this way. So s orbitals are on the first energy level, p orbitals happen on the second, d orbitals start on the third, and then obviously here, f orbitals start on the fourth energy level. And that's how you can recreate that. You just go, okay, first energy level, that's where the s's start. Second energy level, that's where the p's start. Third energy level, that's where the d's start. Fourth energy level, that's where the f's start. And then you can just fill in the rest of it like I did over there, you know, knowing that n goes to 1 to 7. So you could kind of go down, you know, in order and kind of fill the rest of it in like I did before, you know, 3p, 4p, 5p, and so forth, 4d, 5d, 6d, and 5f. So you can see, you could kind of, if you remember where the orbitals start or those subshells start, this is the order that you could create really quickly to help you write electron configuration. Question on that there. Okay. So I think this is a good stopping place for now. And I'm going to think about it, but I think we may continue lecturing in lab just to maybe finish this chapter. And I'm going to look at the schedule. So we may not do the experiment today, the scheduled. We may push it to Monday and just maybe finish up lecturing on this chapter just to kind of keep us on pace because the experiment involves some of the stuff towards the end of this chapter and stuff like that. So we'll stop here for lecture at this moment. A couple of things before you go off for our little break here. Up on our Canvas site should be the recorded lectures. That's where you'll find them in the module section. I apologize. The first couple lectures didn't work very well. So the first real lecture is not going to really be up there because it didn't actually record. Some weird setting was off or something like that. So the one we did, I think yesterday, is up there for sure. And then obviously this one will be up there as well at some point. It just takes a little bit of time to get it and upload it, but it'll be there. You can find it in the module section. If you want to watch these again, if you need to be put to sleep or something like that, you can't sleep, you want to watch it again, you can do that. And also up there now should be all the stuff for all the exams. So they're broken up by exams, exam 1, 2, 3, 4, however many we're taking. And under there, you'll find some review material, and you'll also find the homework problems that you need to do for each of the exams should be listed underneath there as well. So that stuff's up there, so make sure you take a look at it. All right, we're going to take a little break, and then we'll head over to lab. And like I said, I think we might just continue lecturing today. I'll let you know when we get there. Before you take off, though, if you didn't write here in the chat box for your attendance, please do so. And otherwise, I'll see you in about 20 minutes. Yeah.